Hello, this is Scott Dahman of PowerWorld Corporation. In this section, we'll take a look at some of the advanced features of PowerWorld Simulator's contingency analysis.
The basics, just setting up a contingency analysis and auto-inserting or manually creating a contingency, is covered in our other section called Introduction to PowerWorld Simulator, and it's just the basic contingency analysis. Here we'll discuss some advanced tools and options that allow you to solve contingencies in different ways. Limit monitoring, of course, there's limit monitoring settings in Simulator that govern the power flow and a lot of other things. Within contingency analysis, you can have it make some adjustments to what gets monitored as a post-contingent violation. We have also a construct called monitoring exceptions, where you can tell it to ignore certain pairs of violations and contingencies, or to include them where they would otherwise be ignored. Custom monitors is a way to keep track of flows or voltages at certain locations in the system during every contingency, regardless of whether a violation is reached. Load throwover records allows you to model some distribution switching actions. And then you can do different things with generators, have them behave differently in the post-contingent state than they would in the normal power flow. There's a screening tool, which if you've got a large list of contingencies and you're using a full AC power flow, it can take a really long time to run through it. The screening options allow you to do a linearized DC solution for all the contingencies and then only pick the worst ones to run a full power flow solution on. You can have switch shunts do different things in a post-contingent state similar to generators. And if there's any option that's not present in any of these standard modes for altering the behavior in the contingency analysis, you can throw stuff in an auxiliary file. And we'll also look at varied ways of looking at results and contingencies. Combined type tables is helpful for sending things out to Excel, or just for looking at everything in a single table instead of a series of related tables. Report writing, you can dump results out to a text file, which you can load into Word or something else. Comparing two sets of contingency results, we're not going to dive into that so much in this section because we have a really detailed example in a later part of the training. And then we'll also look into doing conditional contingency actions, things like model conditions, model filters, and how you can use those to build remedial action schemes. This is a huge topic. We'll just kind of scratch the surface and give you the tools to understand that it's there. And then there's an appendix, which just gives you some ideas on, if you do need to build remedial actions, how you can use some of our sensitivity analysis tools to make that easier. All right, so this is an example case we're going to be using. This is a synthetic case, which is we have on our website. It's freely available to download. It's called Active SG25K. The 25K represents 25,000 buses that are in the case. And it should be in the top level. And so here's the one-line diagram for it. And what we're going to do is go into the Tools ribbon and open our contingency analysis. Okay, so we're going to start just by auto-inserting some contingencies. So I'll click down to the auto-insert button in the lower left. And I'm going to keep all of these defaults except for I'm going to use area zone filters to look only at the area Connecticut. So opening my area zone filters, I'll just go to the shown column and toggle everything no, and then double click on the shown by Connecticut. which is area number 23, or if you sort it by the area name, it's near the top for that. And then I also want to filter on voltages to only look at 200 kV and above. This will limit the number of contingencies that we insert to a manageable number. And then with those options, I'll click Do Insert Contingency Record. The first thing I'm going to do is just, before I use any advanced options or limit monitoring or anything like that, I just want to run the contingency analysis, and we'll see typically if you go in and run the contingency analysis without setting these options, you're going to get a lot of results and violations that you don't really care about. So we'll then proceed to look at ways that you can filter some of those out. So if I go to the Options tab, I just want to make sure that my calculation method is set to linearized lossless DC so that I can get results relatively quickly. It is right here, so that's good. If it's not, then just check that middle one right there, and then we'll click Start Run. Expand this a little bit. We have a whole bunch of violations for all the contingencies. There's a ton of them, and there's you kind of get the same numbers as far as number of violations, and the maximum branch overload is very similar no matter what contingency you go to. You select several of these contingencies and you're seeing the same numbers and the same violations for a lot of them. And the reason is that those are generally base case violations. Now, there's several things you can do to clean that up. One of the things that you might want to do is just go to your limit monitoring settings to begin with and only zero in on the parts of the system that you really care about. Even beyond doing that, you still might get a bunch of overloads that are even in the area that you do care about. Like if I just look at some of these results for some of these contingencies, I've got a bunch of overloads in Tennessee. We only inserted outages that are in Connecticut. These are just base case overloads that keep getting re-reported. So we might want to ignore those. So if you go to the Options tab here, under Limit Monitoring right here, if we expand that, there's a page called Advanced Limit Monitoring. And clicking on that, on the right-hand side, I can see that there's several different options with respect to base case violations. And the default is to just list all the base case violations for all the contingencies. So every time it runs a contingency, if you've got these base case overloads, unless you have this unique situation where the contingency actually clears the overload, then you're going to keep seeing the same things pop up over and over. This first option here is just do not report base case violations. So if anything violates the contingency limit in the base case or in the reference state, then it simply wouldn't be reported for the result. And then the third option down here is something of a hybrid. It's saying to ignore violations if they are under a certain threshold of severity. And that threshold you can specify for lines and transformers, for bus voltages on the low side and on the high side, and also for interface flows. As we're just doing a DC power flow here, and we don't have any interfaces in this case, the only one that's really applicable here would be the first one. But for example, I could put in a number, like say 2%. Anytime a contingency causes an overload that is less than 2% change from the reference state, it wouldn't be reported in the results. So we can see the effect of that either by rerunning our contingency analysis, or there's another shortcut that we can talk about here, another trick. If you do anything that changes the limit monitored set of elements to make it smaller or more restrictive than it was when you last ran the contingency analysis, you can tell it to just filter those results out that are no longer being monitored. So that's under this other tab, and there's an option for filter results using the limit monitoring settings, basically using the current settings, which you may have changed since you last ran the contingency analysis. And if I do that, I'll see most of these violations disappear. So there's nothing popping up in here in Tennessee anymore because line outage distribution factor for outages in Connecticut doesn't really impact stuff in Tennessee, so we don't see that. That's one way to take care of that. Of course, another way to take care of it is you could go into your limit monitoring settings and tell it to ignore everything except Connecticut. And actually, in a later stage of this example, we'll do just that. But wanted to just show you the advanced limit monitoring option too. So yeah, this slide just shows like when we initially ran the contingency analysis, we ended up with a bunch of base case violations that get re-reported. This explains what you can do with the re-reporting of base case violations. And then this is the option that we took by setting a threshold of 2% to not report if the change is less than that. And then this just explains how you can use the filter results using limit monitoring settings option under the other tab to clean those up. On the left side of the dialog, we're not going to go through specific examples of this, but you can also tell it to never report violations if the change is small enough, or to always report as a violation if a change in a flow or voltage is greater than a certain threshold. And that can be useful if you just want to understand which contingencies have large impacts on elements, even if it doesn't create an overload, but rather just creates a big change in flow or a big change in voltage. That's the second option, always report as a violation. Never report as a violation if the changes are small enough. This would address things that are not necessarily base case violations. Like the option that we looked at before only addresses what happens if there's a base case violation. You can also have situations where there's not a base case violation, but a very small change pushes an element into an overload. And if the change itself is very small, then you might conclude that the contingency didn't have a huge impact, so therefore you don't want to see it as a violation. And that's what this never report group is. And at the bottom, for voltage analysis, you can have it report changes in bus DVDQ sensitivity. And I'll switch back over to simulator. Options, advanced limit monitoring. If you choose that, then there's a couple different parameters. One is the change in DVDQ sensitivity multiple. With this option, you have to use the full power flow calculation method. Of course, if you're doing a linear solution, then it's not going to solve for voltages and it's not going to know the DVDQ sensitivity. But with the full power flow calculation method, what it'll do is it'll calculate the self-sensitivity DVDQ value at every bus that meets the filter that you use. The filter is optional, but it's strongly suggested that you use it because otherwise it just really slows down the calculation process. For example, you might want a filter that looks just at load buses and maybe within a certain nominal kV range, for example. And then you'd apply that advanced filter there, and then you'd put the sensitivity multiple here, and then it would compare for those buses that meet the filter, the reference state or the base case DVDQ sensitivity, and then also recalculate the DVDQ sensitivity after each contingency, and then anything that exceeds that multiple would be reported as a violation. We will get into some examples with that in a later topic too, where we look at generator interconnection. And then there's just a simple checkbox where you can report as a violation anytime a bus becomes disconnected by a contingency. This slide right here just indicates that some of these options, primarily the ones on the left side of the diagram, also belong to limit groups. within limit monitoring. And if you apply those options to a limit group, then that would override the options shown on the contingency dialog for that limit group. Just to show you where that is, if I come back over here and I open my limit monitoring settings from the tools ribbon and I look at my limit groups, I can show the dialog on a limit group, and there's a contingency options tab which has the same type of parameters on it. And if you check the box and then you set the parameters, then these would override whatever settings you have in here, would override the similar settings in the contingency analysis for that limit group. Okay, so the next topic we'll look at is called monitoring exceptions. You can tell it to include or exclude certain pairs of contingencies and monitored elements. And what this is useful for is kind of a shortcut to doing a complete remedial action scheme modeling. So for example, if you know a certain overload that occurs in the contingency analysis is not a real problem because there's some sort of remedial action that alleviates it, but you don't want to model that explicitly, either because it's unknown or because it's too complicated or involved. You can just simply tell it to ignore that monitored element during that contingency, and it would still be monitored everywhere else. Alternately, you can use this tool if you have your limit monitoring settings set up to monitor nothing or a very limited set. You could use this tool to tell it only things that would be monitored. So certain monitored elements during certain contingencies, you would use the monitored status of include. So we'll just do an example here that applies directly to the results that we've already generated, and that would be to exclude the Seymour Walcott 100 kV outage, or I'm sorry, monitoring of Seymour Walcott 100 during the outage of Bethel to Danbury 230 kV. And this is one that this is a particular contingency that we'll dive into a little bit later, and we'll look at just solving that specific contingency and looking at the one line diagram. What I can do is go to my contingency results, and if I scroll down here, I think it's the 100th one in the list in the default sort order here. It's the outage of Bethel Danbury 230 kV. So here's the action that's included within that contingency, and I have two violations here. And the most severe one is this Walcott to Seymour, where I've got an overload of about 120%. And let's just say there's some remedial action scheme that I know alleviates that, so I just don't want to see that result. But for other contingencies, if there's an overload on that line, then I want that reported. So I can tell it just to ignore that one with a monitoring exception. I'll go over to my options, and I'll go to monitoring exceptions, and then I'll right click in here and then insert. And what you're really defining here is a pair. So at the top you specify a contingency, and I'll just hit change on that, and I can use like a wildcard search if I want to jump to the Bethel outages. There it is, Bethel Danbury, that one right there. And then the bottom part of the dialog is to specify either a bus, a line, or an interface that you either want to exclude or include. So exclude means ignore it during that contingency. Include means always monitor it during that contingency, which could be useful, again, if you've got a situation where normally you're not monitoring a certain line. Apply my area zone filters here, and I'll sort this by name, and then I can easily find the Seymour to Walcott 100. That's this guy right here. And then the status I'll set to exclude. So the three options are include, exclude, and default. Include means always monitor it. Exclude means always ignore it. And then default means use whatever the default monitoring is for that element. Essentially means ignore the monitoring exception. So you can create the monitoring exception initially, and then if you want to toggle it off, you could just change the status to default. So if I have it at exclude right now, then what I could see is that if I go back to my list of contingencies and again filter out according to the monitoring exceptions, then I should see that one disappear. So, and it does. And so now I'm just left with this other one. But again, if there are other contingencies that would cause overloads on that particular line, they would still be reported. Just ignore it right here. So we'll take this example and we'll develop it more with an actual remedial action scheme. And we'll do, the solving of the individual contingency in the full power flow mode to get into more detail with that. And this other construct here is called custom monitors. And what this can be used for is if you just want to know, say, the flow on an interface or the voltage at a bus or the flow on a line during every contingency, regardless of whether or not it's a violation, you can set up a custom monitor for it. This can be useful for things like if you want to set limits for interfaces. You can identify, which flow values on an interface correspond with other violations that you might want to, for which you might want to use the interface flow as a proxy. We can use the example of the line that we just looked at, the Seymour Walcott one, and just track the flow on it for every single contingency. So we would come over here to our options and we go to custom monitors and we'd insert that as a custom monitor. And then we'll give it a name later. But what we want to do is we'll pick out a specific object. You can also use all objects, but then you would probably want to put a filter on it so that you don't really track everything in the case. We'll just do the simple example where we care about a certain object. And we'll choose the element type branch. And then we'll do Seymour to Walcott. That is the direction we wanted, right? Yeah. This one right here. And then we'll choose a field. We'll look at megawatts. If I just start typing that, it jumps to the megawatt group. I'll choose the maximum. So that could be either on the from end or the to end, whichever one is higher. And then there's some other advanced options here where you can only report if the change in the value is greater than a certain amount. But for this simple example, we'll just monitor it everywhere. And then we click OK. Oh, and I gave it a name, new custom monitor. If I want to change that, I can double click in there. Call it, for example, Seymour Walcott 100 kV. And then in order for these to actually be calculated, you also have to use the full power flow calculation method. So we'll go back to the modeling basics and just change it to full power flow. And I'll just let it run through a few contingencies because this is kind of a slow process. And I'll stop it after it solves about 5 or 6 contingencies down here. So we'll just pause it and then abort. It's fine. And then if I go to my results, then if I go to my contingencies tab, I can see these are the contingencies that it successfully processed before I stopped it. We've got a few violations here. If we want to see our custom monitor results, we would go to the results and then go to custom monitors. And then we can see, we can choose, if we created more than one, we can just click on the ones that we want. And then it shows the value of the flow during each contingency. The reference value is the base case value. And we can see some contingencies cause the flow to go up. Some of them actually cause the flow to go down. And then the change in value. So Again, that could be kind of useful if you wanted to know what flows on a line or an interface correspond to other violations, and then you could set a particular limit or an emergency limit for that line or interface that corresponds to safe operating limits for other points in the system. All right, so the next topic we'll look at is called screening. And as we saw when we tried to run the full AC power flow, if you've got time to run the AC power flow on all your contingencies, usually that's the most comprehensive way to get detailed results, and you can solve for voltages. If your time is limited and you want to get some quick answers, you can run the DC power flow, which is what we did initially, but then that doesn't give you all the details on those contingencies. Kind of a middle of the road approach is to use the screening, which will look at the severity of the contingencies using linear methods and then run the full AC power flow to solve only the worst ones. And so the first thing we'll do is we need to go into our limit monitoring, and we just have one group. We just have the default monitoring group in this case because we haven't set up any others. But we'll restrict our limit monitoring, first of all, to only look at area 23, which is Connecticut. And then we'll also look at 100 kV overloads and above, and we'll ignore radial lines and buses. Yeah, and then we'll also ignore the lines that have base case violations. When we run when it does the screening, it'll only have a rank value, which we'll see what that means in just a little bit for those that are overloads that are caused by the contingencies. So I'll switch over to simulator here. I'll go to my tools, limit monitoring, and we'll go to the area reporting tab to restrict the reporting to look only at Connecticut, which is area 23. So here in the report limit columns, I'll set everything to no except Connecticut. I'll just toggle that back to yes. You can do it from the drop down. And then for the report minimum KV, I'll just set this to 100 for every area. And I will ignore the radials. And I have two lines and transformers that are base case violations. For purposes of doing this screening, I'm going to tell it right here in limit monitoring to just not monitor these two. So change the monitor to no. What I'm looking at is just the violating elements right here. So if I set those to no, if I refresh the display now, then those would go away. Yeah. So now I have nothing that's shown up as violating. And then I'll go to my modify create limit groups setting and then right click on that and show its dialog. And then there's a tab in here called contingency screening. So I'm going to set the branch tolerances to 100% of the limit. What that means is that any contingency that causes an overload of 100% using the linear solution method, it'll give that a score, a rank for that violation, and then that can be used to judge which contingencies get solved in the full power flow method. So these are the steps that we just took in the limit monitoring settings. And then in contingency analysis, under the DC and screening options tab, we'll set the screening option to screen only and then uncheck the include voltage. And what this will do is it'll run through only the linear lossless DC method, and then we'll be able to see what the rank is of all the contingencies in terms of their severity. And then that's going to be used then later to determine which ones get the full power flow solution. So come over here. I'll just go ahead and close my limit monitoring. And then in contingency analysis, I'll go to options, DC and screening options. And then for use screening, I'll do screen only, decheck include voltage, and we'll screen with the linearized lossless DC. And then I'll come back to my contingencies, and then I'm going to go to my display column options and show. Just type in calculation in the search box right here, and this is the field that I want right here. Calculation method. I want to show the calculation method, and then under screening, the rank for the branches. The other step I need to take is to tell it for each contingency to allow screening. And I'll just do that for all the contingencies. There's a contingency field here, screen allow. And I want to set that to yes. Try that again. Okay. Now I get a bunch of results that's based on the linear solution. So if I sort, I'm sorting in descending order here by violations. I can also sort by screen rank and branch. And what that is it's like a composite of megawatt overloads for the branches. So if you have more violations, or if you have more severe violations, you'll end up with a higher rank right here. And if I scroll down, with these settings where I have no base case overloads and I'm screening to 100% of the flow, if I have no violations, then the rank is 0. So this just shows you the process by which it does the screening. Now, if I actually want to do an AC solution for some of those contingencies, what I would do is I'd come back over here to the options and the DC and screening options, and I'd choose the use screening. I'd change that to yes. And then I would screen, I'm going to just change this to 10 branches. What this means is it will do up to 10 contingencies with the full power flow solution. Yeah, I want to come back here and make sure I've got my calculation method set to full power flow, but then also to do the screening. So now if I restart this, it does the fast screening on all 248 contingencies, and then it goes through a second process where it actually solves the contingency with the full AC power flow, but only on the 10 worst for the ones with the highest branch screen rank. And those are here. If I'm sorted on descending order on screen rank right here, I can see that for the first 10, then it gave me a full AC power flow solution method. 3 of them actually didn't solve. So the power flow failed to converge for those. So I really don't get any results. But for the other 7, I get complete results, include the AC power flow with the reactive VARs. And I've got my branch MVA overloads. Plus, when it does the full power flow solution, we still have that custom monitor in there. It reports the value of the custom monitor as well. Okay, so this is just kind of the summary of how it works, which we discussed, what the screen rank is, and that it's going to do. It did up to 10 contingencies based on the branch rank. And then these are the results that we got. All right, the next set of options we'll look at is called Generator Post-Contingency AGC. And this allows you to either allow or prevent the response of specific generators. And you can have it be different in the contingency solution than it is in the power flow solution, if you want. So if I go to my options, we've looked at basics and we've looked at DC screening options. The next thing down is called Generator Post-Contingency AGC. And this just gives you a list of all, this is just a generator case info display that has specific fields related to Post-Contingency AGC. You see all the generators. You see this is the primary AGC field, which is set to either yes or no. This is going to apply to the power flow. And normally it's going to apply to the contingency analysis as well. But if you change the settings over here in these two columns, then you can have it be different. This is the participation factor assigned to the generator, which works in the power flow and also in the contingency analysis, unless you change this column right here. So the first column is called Post-Contingency Prevent AGC Response. So there's a yes-no logic here that's kind of opposite of what you have here. Like over here, if a generator's AGC field is set to yes, that means it's AGCable. If the post-contingency prevent AGC response is set to no, that means it'll use whatever AGC setting is indicated for the power flow. It'll do the same thing in the contingency analysis. You have an option that is a yes, which would essentially turn AGC off for that unit in the post-contingent state. So if you wanted to block the unit from responding to the contingency, you would set that to yes. If you wanted the unit to respond during the contingency, even if it's blocked during the power flow, the third option of respond does that. So even if you have the AGC setting set to no for the power flow, that unit would be available to provide makeup power in the post-contingent state. So that's the third option. I'm just going to set these back to their defaults. And then you can also put in a different participation factor for the post-contingent state. So if I wanted this unit, for example, to provide proportionally larger participation factor than it does in the power flow, I could put in a larger number there, say a number of 10, which is bigger than the power flow participation factor of 1.6. In a post-contingent makeup power situation, it would then provide more makeup power than it would in the power flow. But if you want everything to behave the same, and you would just leave the default of no for everything here and same for everything there. Okay, so the next option is bus throwover records. And this is intended to model distribution switching. So typically in a power flow case at a transmission level, which is what people normally work with in Power World Simulator, we see distribution feeders represented as loads. So I'm going to switch the area zone filters on here so we're only looking at Connecticut. And just as an example, if we go in here to the New Britain set of buses, if I load this one up here on the bus view online, just right click and bring that up. You can see we've got a 100 kV bus here and a load sitting on it. And in real life, this probably represents a distribution feeder, and there's a network behind there, a distribution network behind there. It's probably a step down transformer and some other lines. And that much load is normally connected to this bus at the transmission level. But if something happens, like say this line goes out of service right here, if we take that out, then that load becomes disconnected. And what might really be happening, I can solve my power flow again. What might be happening in the real world is that some distribution breakers that are normally open might close, and then this one might open so that those feeders get connected at a different bus. And there's no way, without changing the topology of the model, you can't explicitly do that in the power flow. But in the contingency analysis, we give you this option where you can specify another bus to be the throwover bus. And let's just say that 230 23041, that load gets put over to 23044, which is a similar looking. If I right click on this, look at the bus view, it's a similar topology where you've got a load that's modeled at 100 kV. And so you could have those, if they're really connected at the distribution level, that detail is not in the model, you could just specify that those loads get thrown over to each other by typing in a bus number there. If you've got a record in here where, let's say you create a record and you want to delete it, the way you delete it is you just put in a bus number of 0 and then hit enter. That's explained on the slide. And then it goes away. So you put in a valid bus number and then it would call up this other information like the name and KV. So here it's depicted on the slide with 2 different bus view 1 line diagrams, and you can specify basically just putting in a bus number. All right, the next thing on the list is called generator maximum megawatt response. With that, that's another list of generators, kind of like our generator post-contingency AGC display was, except it just shows some different fields. This has a list of generators, and you can put in a megawatt value for each generator. It's a bidirectional value. So if I put in a value of a 100, let's say, for this generator, it means that in the post-contingent state, if makeup power is needed, that generator could respond up or down by a maximum of 100 megawatts. So it'll cap that response in the post-contingent state. So if you want to not use the option, then you basically just leave them blank. And if I enter a space, you don't want to put in a 0 to get rid of it, because that would basically make the unit not respond at all. But if you just put in a space and enter it, then you can delete values. The next thing is called line drop and reactive current compensation. And we have a couple good slides that just explain exactly what that is. This is for the generator voltage regulation behavior. And normally in the power flow, each generator is set to regulate voltage at a particular bus. It could be the local terminal bus, or it could be a remote bus, but it's varying its reactive power output to try to hit a voltage set point at a specific bus. You can also tell it to regulate the voltage at a specific impedance away from its terminal, so looking out into the network, where the point that it's regulating corresponds to that impedance level rather than a bus in the network. And you can set the real part of the impedance, or the R value, and then also the imaginary part, or the X value, the reactance, you can specify in the table. And the terminology that's used in industry is either reactive current compensation or line drop compensation, depending on whether the impedance is greater than or less than 0. So if it's less than 0, it's like looking inside the machine. If it's greater than 0, it's looking out into the network or down a transmission line. So this is how it's depicted graphically, with a little 1-line diagram with a cloud representing the rest of the power system. So we have a generator, its terminal bus, and it can regulate that terminal bus. It can regulate a remote bus, or it can regulate some fictitious point that's out into the network at an impedance of R plus JX, where R and J are the values that you enter in the table right here. R and X, J meaning the imaginary number unit value. And then if you want to use this option, the default is to not use it, in which case the generator would be regulating whatever bus is specified with the generator record. Or you can choose to use it always in both the contingency analysis and in the power flow, or you can tell it to only use it in the contingency state, the post-contingent state, which is the third option. The next option is called the switch shunt post-contingency. And this just gives you a list of switch shunts, so capacitors and reactors that are in the network. And I'm going to apply the area zone filter to the display, so it looks just at the Connecticut ones. There's just a handful of those, 25. But anyway, this just shows you some of the settings. So these are all in discrete control mode, it looks like. If you want, of course, more details on how many blocks are available or whatnot, the best way to do that is probably to look at the dialog for each individual device, and it'll tell you the number of steps in megavars per step in each block. But here, you can specify a different control mode in the post-contingent state. So default means just use the same thing that it uses in the power flow. But if you want a different control mode in the post-contingent state, you can pick that. And then also if you want different voltage regulation limits in the post-contingent state, you can choose that and then change these values. It populates these by default to match these values right here, which are the power flow values. This is the current voltage at the regulated point, so which is read-only, of course. But if you want to put different regulation limits in terms of voltage in the post-contingent state, maybe you wanted to, relax voltages if during a contingency, you could put in a wider range. And then also the minimum and maximum megavar output. So if you wanted to, let's say, maybe it takes a long time to change, to switch in and out a block, maybe takes some time. So you want to restrict how many megavars can go. You can put in different minimum and maximum limits, and it's going to populate it by default, matching what's available for the device based on the power flow. But if you want to make that a more restrictive range or something, you could do that. And then, so every screen that we've looked at up to this point in this little section here, under these modeling options, gives you different ways that you can have the post-contingent state behave a little bit differently than the power flow. There's another page called Auxilary Files, and if there's some settings that you want to change that aren't available on these screens, you can just place them in an auxiliary file and then point to that auxiliary file here. So there's two different options. There's a post-contingency auxiliary file, which would apply basically before the solution is done. And then there's a post-contingency solution auxiliary file, which would get loaded after the contingency is solved. That could be used, for example, to save data to a file from that auxiliary file. There's a note in the slides that just says, you must only change values. I guess that's not true. You could change whatever you want, but you should only change values that are stored as part of the reference state, because what happens in the solution process, at the beginning of each contingency, it'll restore the reference state, then it'll load the auxiliary file, then it'll solve the contingency. It'll load this auxiliary file, then solve the contingency, then load this auxiliary file. If there's something in there that's not stored as part of the reference state, then you would alter the case. If you alter things that are stored as part of the reference state, then you would get generally desired behavior, because then when it goes to the next contingency, it would restore that reference state. So there's a summary slide in here which just shows an example of things that are stored in the reference state. So these are the kind of things that you could put in the post-contingency aux file that would be okay, because it would restore. Like, for example, maybe during a contingency you have a specific set of generator reactive capability curves. You could store those in an auxiliary file, specify that file to load, and then it would use those capability curves for every contingency. But then when it's done running contingency analysis and when it restores the reference, then it would take you back to where you want to be. So if you alter anything in the case that's not part of this set, then you could be changing your case permanently, or at least changing what's stored in RAM. You'd have to reload the case from the hard drive in order to get back to where you really wanted to be. All right, next screen refers to transient stability models, and I won't spend a whole lot of time on this, but there are certain like relay models that are in use with the transient stability tool that can be applied to the contingency analysis. So if those relay conditions are met during the contingency analysis, you can actually have them trip. And for each class of relay, the default is to ignore them or not use them at all. But you can choose to trip and take an action if that relay condition is met, or that model, rather that model is met, or you can have it just monitor what the relay is monitoring. And if it does that, then it would just report as a violation, a transient model violation in your contingency result, but it wouldn't take any action. It wouldn't open a line or open a shunt or whatever. And these are the only ones that are available. And there's a maximum time delay to consider. Basically, it would only trip only transient models that have pickup times less than that value that you set up there. And then finally, you can store contingency results to a hard drive if you want. The default behavior is just to store everything in RAM, but if you have a really, really large list of contingencies that are likely to produce a lot of results, there could be a risk that you exceed your memory capacity on your machine. So that's here on result storage. You can tell it to write to the hard drive, and then you can pick a file name, give it a name and a location to write to, and then down here it tells it what types to send out. If you click add defaults, then it just tells you that for each contingency violation, it'll write out the name and the values and the associated limits and these other fields in this order. So those will get written out to the auxiliary file. If you don't need that, in our example, we don't really need that, so we'll just decheck that box, writing to the hard drive. These next few slides talk about what we call combined tables. So a lot of the results and also kind of the input data, like the actions, the violations or the actions that belong to a contingency, we normally browse those by looking at related tables. So if I go to my contingencies and I click on a contingency, I can see the actions. You can have one or more actions that's part of that contingency, and you can also have one or more violations. So really, I'm like browsing 3 different tables in order to get all of this information. If you want to put like certain combinations of 2 of those tables into a flat file that you can either just look at in one file in one space, or if you want to dump it out to Excel or save it to a CSV, then you can do that from what we call combined tables. So if I click on that and I look at, for example, the contingency violation list, this will give me a flat file of every contingency and every violation or violating element and the corresponding violation values in a table. So I have 84 lines here. I've got 3 contingencies that were unsolved. I have 10 of them that were solved from this last example, or yes, 7 of them that did solve. Rather, there were 10 that were screened for the AC analysis. So I've got my custom monitor for the other 7 right here, and then I also have branch MVA overloads that are shown. So of course you can dump this out to Excel. You could save it to a CSV or auxiliary file just in this format rather than having different related tables sent out. I can also look at a contingency element definition. If you wanted to build a list of contingencies from Excel, for example, you could use this format right here to just paste them in to this space. So to see what you could just dump this out to Excel right here to see what that looks like, then take other data that might define other contingencies and put it in the same format and then paste that in. So those are the elements. And then we also have a contingency violation matrix. And here you tell it like what to include in the matrix. And I'm just going to tell it to include everything because we don't have a huge list. And then I'll process it. And then we have rows for every contingency and then columns for every violation. And so wherever there's a value at that intersection, the value is provided. Again, just another way to browse results. If I go all the way over here to the right, I think my custom monitors are, yeah, here's my custom monitor. So was only solved for, again, some of the contingencies because we did the screening. But then other violations are shown in here. And you can browse these if you only want to look at branch violations or only bus violations, which we don't have any, but those can be shown in there. Custom monitors only. So yeah, my contingencies are in different rows. So just different ways to browse the results. And if you want, of course, you can dump this out to a CSV or out to Excel. Okay, what actually occurred, we'll take a look at that later, but you can look at, if you have remedial actions, things that are conditional, that don't always occur, which we'll look at an example later, then that can be a useful display to show you what was applied and what was skipped. And the next few slides just have the examples of what we looked at. You can go to other produce report, and then from that screen, you can just tell it what to include. And then when you go to save the report, then it will only save what's the options that are checked here. Comparing two lists of contingency results, like I mentioned, this will be shown in greater detail in another example that we do later. And then also, if you're using our sensitivity tools like PTDFs, you're looking at a transfer between parts of the system, and then you only want to look at contingency violations that impact that transfer, then you can use this under the other tab, calculate OTDFs using existing PTDFs, and then filter out violations that are less than a certain OTDF. So you can only look at those contingency violations that impact the transfer that you calculated in the PTDF dialog. All right, so next we'll do an example and we'll look at some of the tools that can be used for conditional actions. So thus far, we've talked about contingencies and contingency elements that always occur, meaning every time you run that contingency, no matter what conditions are in your reference state, every action that's defined with that contingency will always be simulated in your contingency. But you can also have actions that are conditional. We have a field called the model criteria, which is it's a condition that evaluates to either true or false, and the actions that are associated with that model criteria would only be taken if it's true. We'll see that this is a useful tool for creating remedial action schemes or special protection schemes that are armed or activated only under certain conditions. So under maybe certain loading condition or certain voltage profile or whatever you can imagine as far as monitoring a condition and then arming an action associated with it. So an overview of remedial actions is it's a way where you can specify groups of actions that could occur under any contingency, but only if certain conditions are met. So there's a field called arming criteria, and the whole remedial action, the whole group of steps would only possibly be eligible to occur if certain criteria is met. And then individual actions within that remedial action would be taken only if certain conditions are met. A really simple example would be line X gets taken out of service only if it's overloaded. So if it's not overloaded, it stays in and nothing changes. But maybe you have a contingency that overloads the line, and then that condition would arm the remedial action that would take it out of service. So as we'll see when we build our example here, you can have individual actions that are grouped. They're like in a wrapper called a remedial action. Or a remedial action is kind of, as we'll see, like a contingency, whereas the individual actions are kind of like contingency elements. Criteria that we can use, we have two different object types in Simulator that can be used as criteria, and we'll do examples. A model condition is the simplest one, and that would be the combination of a specific element and a filter. So for example, if you want to check to see if the voltage at bus 4 is less than 0.95 per unit, that's something that could be expressed inside a model condition. And this will either evaluate to true or false, and if it evaluates to true, then the remedial action associated with it could be armed, or the individual action associated with it could be taken. Model filters are basically logical comparisons of one or more conditions or of other filters. As an example, we'll create a model condition that checks to see if the flow on a line in our system, a line between Waterbury and Wolcott, is greater than 100 kV. And this is one that is overloaded in some of our contingencies. If we go back to this list and we sort this one right here between Bethel and Danbury was one that we were looking at before. And one of our overloads that occurs is from Waterbury to Wolcott. And as I step into this phase of the example, one of the things I want to do is go back to my options and my monitoring exceptions, and I want to skip that monitoring exception. So I could just delete it, or I could change its status to default, which would cause it to go back in. And if I change it to default and I go, let's go back to also our DC and screening options and change use screening to no. So we'll just go and we'll just be doing the full power flow, but we'll only be looking at one specific contingency for the rest of the example. So I'll say screening no, and on the basics, I'll make sure I'm using the full power flow. And then if I go back to my contingencies and I look to this one that's 100th in the list with the default sort order, so I'm not sorting. Just click up here to remove any sort. And then right click on the contingency and go to contingency record solve selected contingency. I'll see that I have these two overloads, plus here's my custom monitor right here. But yeah, Wolcott to Seymour gets overloaded, and also Waterbury to Wolcott. If I wanted to put in a remedial action scheme that kind of addressed this overload, one of the things I might want to do is check the flow on one or both of these lines. And as we'll see, they kind of occur in series. If I go back to my one-line diagram here, and from the one-line diagram, I go to the one-lines menu and open up the saved view for, say, Danbury to Waterbury, right in here. So this is the overload right here, is on these two lines, which are kind of in series. And then the outage occurs over here. This is Bethel to Danbury. So that 230 kV line goes out of service. and then we get overloads on this lower voltage over here. So if I go back and restore my reference state, then here's the normal condition with that line back in service and heavily loaded but not overloaded lines over here. So maybe I have a condition that I want to evaluate the loading in this part of the network. And if it's over a certain level, then maybe I want to take some actions to relieve the loading. So I'll go back to my contingency analysis and then go to options and then go to remedial action definitions. And I'll open that and go to model conditions. And then I have none created. I'll just right click in here and choose to insert one. Like you can do in just about anywhere in Simulator, you can use that procedure. Right click in the grid and choose to insert. I'll just add by number, and I've got on the slide, I have the number of that element. Waterbury to Wolcott is the branch from 23512 to 23370. And I've got bus right here, so I want to change this from bus to branch. Oops, an extra 2 in there. Okay, right here, Waterbury to Wolcott, 100 kV. So there's the element, and then the filter I want to use is the megawatts greater than 50. So I'll choose megawatt maximum, and I'll do greater than 50. And then I'll choose, I want to evaluate this in the reference state also. So a lot of times for arming remedial action schemes, that's done based on a base case or a pre-contingent value. So if we want that to be used, then we would check the box up here to evaluate it in the reference state. I'll choose that and then click OK. And then I'll call it Waterbury Wolcott 100 kV greater than 50 megawatts. And then it's created, and it tells me right here that the condition is met. Model conditions can also be used for line statuses. In the prior example, we looked at the flow on a line, but this can be used to force remedial actions to occur only during certain contingencies or only when certain lines are, say, forced out of service. We might want to check if the line that's in that contingency that we're taking a look at is open in a post-contingent state, and then also compare it to what it was in the reference state. So we can make a model condition that looks at the branch status and checks if it's equal to either open or closed. So I'll come back over here to Simulator and go to my model conditions and then right click in here and choose to insert. And again, we'll look at a branch. So this one right here, Bethel to Danbury, 230 kV. And then we'll look at its status. And then if we want to check to see whether or not it's open in the post-contingent state, we won't check this box to evaluate it in the reference state. We'll just leave it like that. And we'll put a name, Bethel. And we can see that right now that condition is not being met as I'm in my base case or my reference state right now. And then I might also want to check if it's out of service in, or rather in service in the reference state. So this would check in the, not in the reference state. We'll do insert. Again, we'll go to branch. Bethel Danbury 230 kV. And we'll look at the status. Compare it to closed. And we'll evaluate that in the reference state. Okay, and that's currently closed, so that condition is being met. Then what we might want to do is create a model filter that evaluates whether or not both of these conditions are met. So it's open in the post-contingent state, but it was closed in the reference, meaning we're identifying any contingency for which that line is lost, which could refer to the one contingency that we're examining right now. But if we have a longer list of contingencies and we've got, you know, some with multiple elements in it, then the resulting model filter that combines these two conditions would be true anytime any contingency caused the loss of that line, which is really what we're trying to check for with this particular remedial action. So I'll go from here from model conditions to model filters underneath the remedial action definition, and I'll right click and choose insert. And a model filter is really just a logical combination of conditions or other filters. So you can nest these if you want, but we're just going to go one level deep. In other words, we're going to have a filter that references a couple of conditions. So we can pick from the ones that we've already created. We'll check to see if it's closed in the reference, and then we'll also check to see if it's open. And then you can set the logical comparison. I'll have it set to and, which means it was closed and now it's open. And then we'll click OK, and we'll call it loss of Bethel Danbury 230 kV. And this is not presently met because you would have to run the contingency analysis and look at that outage. So here's our list of 3 model conditions that we've created so far, and then this is the slide that describes the creation of that model filter, and we've ANDed 2 of the conditions that we already made in order to create this new filter right here. Okay, so now we're going to build a remedial action, and we've kind of gone through these building blocks right here. What I'm going to do for the next part of it is I'm just going to load an auxiliary file. It'll kind of do the rest of the things, and then we'll just take a look at what's inside the remedial action and kind of step through it. the scenario that we're setting up is that we're going to disable, we've already done this. We disabled our monitoring exceptions that we created, and we'll look at N1, N-1 outages on lines and transformers in area Connecticut at 200 kV and higher. We've already auto-inserted those. We'll switch to the lossless. Well, actually, we did that at the beginning. Here going forward, we're just going to look at the one contingency. So we'll leave it on the full power flow calculation method. But this is what we initially did. We ran it using these limit monitoring settings right here. And if you wanted to load that from scratch, if you hadn't already done everything up to this point, you could load this auxiliary file S04 advanced ctg01.aux, and it would basically bring all of these settings and contingencies in as they're described here. So when we ran it, we saw that for this particular outage, we had the 2 overloads, and we see that already in our results. So we go to this Bethel-Danbury outage. We've got these 2 plus the custom monitor that we created earlier. So those are in there. You can see we have those 2 violations. And this is what it looks like. So we took a look at this already on the one-line diagram also. And if I just right-click and solve that contingency here with the full power flow method, then I can see that on the one-line diagram. And again, I use the saved view, Danbury to Waterbury. So it just takes in this span of network between these 2 substations. And we can see the 230 kV lines in blue and the 100 kV lines in gray right here. So the remedial actions that we've actually started to build, and the rest of which I'm not going to go through manually on the other steps, but they'll be loaded when we load this auxiliary file. What we've started to create and what we'll finish when we load this is multiple layers of actions with different arming criteria that depend on what level of loading is present on Waterbury-Wolcott 100 kV. And again, that's one of the lines in here that's overloaded, this one right here. So they're kind of in series, even though there's another station right here that feeds in. But they're heavily depend. The flow on one heavily depends on the flow on another. So we're going to just set up our remedial action scheme to look on the flow of this first one right here. So if that flow exceeds 50 megawatts, we're going to drop 500 megawatts of generation at Waterford. If it exceeds 100 megawatts, we're going to drop another 500 for a total of 1,000. And if we exceed 100 megawatts, but we're still overloaded after these other actions, then we're going to shed load at Seymour in 10% increments until the overloading is relieved. And Seymour is on the receiving end if we zoom in right here. So if we drop load in this station, if we could calculate the TLR sensitivities if we wanted to get into detail, but you can kind of see just based on this topology, if we cut load right here, then it should relieve flow on these lines, which are coming towards that station. So that's what the scheme does, and we'll load it from that auxiliary file next. I'll come over here, and then I'll click the load button from the contingency analysis, and I'll go into the S4 subdirectory from my training cases, and I'll load this advanced CTG02 file. And when it asks me if I want to delete the existing contingencies, I'm going to say no, because I know what's in this file is really just the advanced options. I don't think it has a list of all the contingencies. So I'll just say no to that. And what I did load, if I look at my message log here, it loaded some remedial actions, some custom expressions, model filters, model conditions, that sort of stuff. Also some injection groups that are going to be used in the remedial action. We're actually going to drop generation from an injection group, and we'll see that there's a few different options on how you can do that. So, whoops, I want to close this here. And I'll go to my options, and under remedial actions, I'll look at model conditions. Here's the one that we already created manually, the Waterbury Wolcott 500 kV. There's a similar one that we just loaded. I didn't go through the steps of manually creating it, but if I look at this dialog, we can see that it's just comparing the flow, the megawatt flow now to 100. So it's just triggering on a different threshold, also evaluating in the reference state. And currently our loading is above that. And actually, yeah, I'm in the post-contingent state. Let me go back to the reference state. So I'll just go to other, restore reference. Some of these switch, but we're still loaded at more than 100 megawatts. So I would expect that if I run the contingency analysis, if this is an arming criteria, then some actions would be taken if they're associated with that, which we'll see in just a moment. So we have these two conditions that we created earlier, and then we have another one that looks to see if Waterbury Wolcott is overloaded. And if I examine that, I believe this one is checked, not in the reference state. This one's going to be referenced in our load shed action, which we'll take a look at. And then the model filters, we had the one, oh, actually this is the same one. I think the spelling is just a little bit different. One of them had a space in it or something. So it's really the same thing. And I have three remedial actions. One of them is called drop Waterford 500 megawatts. One's called drop Waterford 1000, and the other one's called load shed at Seymour. Now, I didn't start to create these earlier. These were only loaded from the auxiliary file just now. And we can look and see what these do. They have arming criteria associated with each of those. And if I double click on that cell, or I click this little ellipsis button, it'll open up a dialog which will let me pick either a model filter or a model condition. And I can see this particular remedial action scheme is armed based on this condition that we manually created earlier, that is checking to see if Waterbury Wolcott has at least 50 megawatts of loading. So I'll just hit cancel on that. So that's what's going to arm this particular RAS. And if I want to see what's in the RAS, the remedial action scheme itself is kind of like a contingency. There's one or more actions that belong to each one. In this example, each one just has one action, but that's kind of like a contingency action. And then each of these actions can also have criteria that are associated with them. You can have more than one action if you want, but in this example, we just have one. So this action for the remedial action scheme called drop Waterford 500 megawatts has a single action of changing an injection group output. And if I show the dialog on this, then I can see it references an injection group called Waterford Gens, which this was also loaded from the auxiliary files, we recall from looking at the log. And it changes it by minus 500 constant value of megawatts. You can also have this refer to a field or to a model expression. We haven't talked about model expressions yet, but there's something in the slides that kind of goes over that. That's, another layer of complexity that you can use in developing these schemes. But in our example, we're just going to use a constant of 500 megawatts. That's what's going to be done. And then we have scale order here, which we'll actually just do the example first to see what that means. But proportional means it'll look at the participation points inside the injection group. There's two generators in here, And one of them has a participation factor of 1 and the other one has a participation factor of 2. So proportional means that it'll grab megawatts based on the participation factor. And when I run this, we'll see exactly what that means. You can also have it go in a certain order if you want with the other options. And it's using the model criteria loss of Bethel Danbury 230 kV. So it would only actually take this action if a contingency caused that outage. So in other words, the line's in service in the reference state and it's lost afterwards. And we'll talk about the statuses in a little bit. This has a status of topology check, which is a little bit different than check. It doesn't involve solving a power flow. There's a slide that goes through these different status options, which we'll get to. But for now, just know that this will be taken during any contingency for which that model criteria is met. So I've got on all of these also, I have a skip field set to yes. What I want to do is we'll just incrementally work with these different stages of remedial actions by toggling the first one, or the drop Waterford 500 megawatts, skip to no. Now that one will be taken as long as the arming criteria is met, and then the actions down here will be taken as long as their model criteria is met. So I'll go back to my contingencies, and I'll right click on this one, Bethel Danbury. And recall when we ran it the first time, we had the 2 different overloads here, and the overload levels are 113 and 119%. If I run it now with the remedial action, go to contingency records, solve selected contingency. Now I get lower. I'm still overloaded, but my percentages are lower. Now let's see why that is. I go back, I'm looking at my post-contingent state. Now I have 109 and 111% instead of 119 and whatever the other value was. This line's still out of service. And what we have here, I can go back to this contingency and I can look at this what actually occurred tab, which we mentioned earlier. And I have 2 actions that occurred. One of them, they're both for the same contingency. One of them was the opening of the line. That was the kind of the main action that happened. And then we have this other action which changed the injection group Waterford gens by -500. That's our remedial action. And it's explained right here. The origin of the action is remedial. And this is what it did. So I can also just open a bus view one line at, let me just look ahead here, 23,470. Okay, if I come over here, here's our Waterford bus at 765 kV, and then I have some step-up transformers and 2 generator buses attached to it. And I can see these are the generators that are in my injection group. If I go to, just take another step back here, I'll go to my Model Explorer and look under aggregations at injection groups. This was loaded from the auxiliary file. We looked at the message log earlier, explained that that was loaded. I have 2 generators in that group. They're both at the Waterford area. One of them has a participation factor of 1 and one of them has a participation factor of 2 inside the injection group. And when we're using the proportional method, like we have set up right now, it's going to get 1/3 of the gen drop from this generator and 2/3 from this, based on those 2 participation factors. I'll close this. Another thing I can do is let's go back to the reference state here. And I can look at Waterford. I've got on both of these generators, I have about 1,081 megawatts in the reference state. And I could also use my difference case tool just to kind of visualize this. So from the tools ribbon, I'll go to the difference case and I'll set the present case as the base case, and then I'll run my contingency again, and we'll see exactly how many megawatts were dropped from each of those generators. I want to right click on this. Again, contingency record, solve selected contingency. So again, now this is the post-contingent state with the reduced outputs on those two generators. And if I go to my difference case and look at the difference mode, I can see that I dropped 167 megawatts from this generator and 333. So that sums to the 500. That's what was in my remedial action step, was to drop the 500 megawatts of generation out of that injection group. And then this shows you where they came from. That's the action that was applied. I'll go back to present mode. Yeah, so this is what we looked at on that particular action in the dialog. The status on that action, again, I mentioned it was set to topology check, which means that it's evaluated after the topology has changed with the line being taken out of service due to the contingency, but prior to solving the power flow. That can be important because if the action associated with this model criteria is so vital that not doing it would result in a failure of the power flow, then you'd want to evaluate it before the power flow is solved. So that's what topology check does. And again, there's more details on those different options for status later. We left this scale order set to proportional. So that means it got the 500 megawatts based on the participation factors in that injection group. We can also try using merit order or merit order open, and we'll do that with different examples here in just a minute. This is what we looked at Waterford with the difference case. We saw that one generator provided 1/3 of the 500 and the other one provided 2/3. And we see from our one-line diagram, and then also just from looking at the results in the contingency analysis, we still have overloading, but it's been relieved a little bit. If we change the scale order option to merit order open, then what it's going to do is it'll go through and it'll actually drop the generators or open them completely. And the merit order will be set by the participation factor. So I think the smaller participation factor goes first. It actually could be the other way around. Yeah, it is the other way around. The one with the larger participation factor is this one. That's the one that'll end up going first. So we'll come back here to simulator and we'll go to our contingency analysis options, remedial actions, go here, and then we'll show the dialog on this action here. And again, instead of doing proportional, we'll choose merit order open. And if you're opening them all together, you can choose to have it not exceed the amount or allow it to exceed the amount, because the amount is 500 megawatts. And depending on what the present output of that unit is, opening it could result in going over 500 megawatts or not. And if we choose do not exceed amount, then it actually won't do anything because both of them are at 1,081 megawatts in the base case. So this wouldn't do anything. Allow to exceed amount will just keep dropping generators in the injection group according to the highest participation factor first until it gets at least 500 megawatts, which in our case should just involve opening one generator. So now, if I go back to my list of contingencies, I right click and I go contingency record, solve selected contingency. And I check on my one line diagram at Waterford, it actually opened this generator. It didn't do anything to this one because by opening this one, I got at least 500 megawatts. So it didn't have to do anything here. and we are driving slightly more than we did before. We get slightly lower levels of loading right there. So that's good. That's merit order open. And then we can also we can add in the second remedial action, which is called drop Waterford 1000. Then what that'll do is it'll reduce the output by another 500 megawatts with the higher arming threshold. So based on 100 megawatts of flow on that line. So we'll choose this to not skip. And what this action does is it just does another 500, and it does it by merit order. And if I'll switch the other one to merit order too. What it'll do is it'll just back it down. If I don't do merit order open, it'll only be able to back down to its minimum. Switch this one to merit order too. And then solve this again. It's going to be similar to what we did before, because last time we actually, with the merit order open on the one action, we ended up dropping 1,081 megawatts. Now it looks like what ended up happening is we dropped this one down to its minimum because it has the higher participation factor. So that one's sitting on its minimum now, and then it went and grabbed the rest of the megawatts from here. And if I look at my difference case, I can see the total dropped is 1,000 megawatts. I got 500 from each remedial action scheme. So it does that accounting between the two remedial action schemes to give you 500 from each one, or a total of 1,000. That's still not enough to completely relieve my overloads. But now if I look at what actually occurred, I ended up with 2 remedial actions now. And each one of them gave me a reduction of 500 megawatts from that injection group. But then the last one, if I look at this remedial action, it's called load shed Seymour. And I'll change its skip to no. And it's going to use the same arming criteria as the 1,000 megawatt dropping. And I will look at this dialog. What this does is it references the element type load at this bus right here, Seymour, with load ID 1. And it drops it by 10%, change by a constant minus 10%. And it has a post-check status. We'll talk about that later too on the slide. But post-check really means it's going to evaluate after other actions have taken. So it's going to do the gen drop and then solve the power flow and then see if the condition is met. So it's only going to drop the load if the other remedial actions don't take care of it first. It also has this checkbox option called persistent. And what we'll see what that does is it'll keep repeating this action of dropping 10% of the load until it either runs out of load to drop or until the model criteria is no longer met. And we'll see that has a result of actually clearing the overloads. Let's go back to our contingency and we'll solve it once again. And now if I look at my violations, I see there are none in the list. This is just the custom monitor value. So we don't have any overloads right here. We have no violations. And if I look at my main one-line diagram again, I can see here, this line's out of service, and we have now no overloads. So what actually occurred, go back here, it went through and it dropped 10% of the load. It actually needed 4 blocks. That's what the persistent action did, was it just kept repeating that until the criteria was no longer met. And again, the criteria was looking to see if this condition was met, water barrier Wolcott 100 kV overload. And it has a status of post check, which we'll again talk about in just a minute. With all of that remedial action scheme process going on, the contingency doesn't have any overload. Here's the action that we just did. It's post check status and it's persistent, which means it'll just repeat. This is with just a 500 kV drop, but it was with the generator open. So this is actually a little bit different scenario depicted on the slide than what I just did. This shows the merit order open for the one. So instead of dropping 1,000, it actually dropped 1080 megawatts. And in so doing, it only needed to repeat the persistent action 3 times. So in the generation drop, it uses an injection group. As I mentioned, when we looked at the 2 different stages where we were dropping 500 and then dropping 500 more for a total of 1,000, even though those were in different remedial actions, simulator was able to do the accounting to allow no more than 1,000. It normally doesn't allow it to exceed that amount. If you want to remove that and kind of make it, a dumber process, you can go to Options, Basics, and click this Disable Gen Drop Overlap. So then it wouldn't be able to check between different remedial actions to make sure that it's not exceeding the total amount. But I think normally you would want that unchecked. Just as an aside, this is for kind of our customers in the West that use the WECC RAS files. You can save contingencies out first to an auxiliary file format, and then you get all those options as far as what to save or what not to save. We also have a WEC contingency and RAS file, and if you choose that, it'll save exactly the contingencies and the model conditions and the remedial action schemes that are needed. There's some details on our website about that format. Okay, we looked at the what actually occurred. We can also examine our message log to see what happened when it starts the contingency. It opens the line from Bethel to Danbury because that's part of the main contingency definition. And then it does these different remedial actions as needed. The first one drops some generation at Waterford, and then it has to go through a process of finding the makeup power, and then it goes through the other remedial action schemes. So cycling through the persistent load drop action is shown here. And back in simulator, so this is the end of the process. Again, in my example, it had to do it 4 times because I dropped exactly 1,000 megawatts and I didn't use the merit order open. But up here at the top, okay, this is where it's having to find the makeup power because of the gen drop, and slightly above here. Yeah, here's the top of the process right here. So for solving the contingency, oh yeah, I left that switch shunt option in there. It did the gen drops right here for merit order, and then here's the makeup power, and then later on you get the load shedding iterations. As I mentioned, there's different status types for the model criteria for arming and also for the individual actions. Check, always, and never are pretty straightforward. They mean that if the model criteria or the arming criteria is true, then the associated action would be taken. Always means it'll always take the action regardless of whether or not the model or arming criteria is true, and never means it'll always skip the action. So those, if I go back to my remedial action schemes here, if I choose always or never, well, yeah, it should probably gray this out even with always, because it's going to ignore the arming criteria and always take it. And if I do never, it's going to do the same thing. It'll ignore this and it'll always skip it. So we normally want check with those, but again, if we want to temporarily disable them, we could do that, or we could also temporarily disable them by toggling their skip field. Yes. For individual actions, we also have the option to do post check, topology check, or solution fail. And those are explained on a sequence of slides here. Post check this is what we used for the load shedding action. If I go to load shed Seymour, this status right here is set to post check. That means it's going to go through kind of an iterative process where it'll kind of do everything else first and then solve the post contingent state with the other actions taken, if applicable, and then it will check to see if the criteria is true and if it needs to take the associated action. So that's shown here. A topology check, as we mentioned earlier, makes it conditional on the post-contingent state after things like the outages are applied, but before the power flow is solved. So that can be used if an outage results in an unsolvable solution. It'll still then be able to evaluate the conditions and then take the action. And solution fail will make the action conditional on the power flow not solving. We're not really using that in any of our examples, but if you have that situation, it'll attempt to go back to the last successfully solved state or the state before the failed solution and then take an action, and hopefully that'll enable the solution to work. Our example didn't really involve time delays, but this can get really complicated. There's some slides that kind of show what that does. It's not actually going to wait. It's just going to look at how the time delays stack up and take actions with the smallest delay. So it's not doing any sort of dynamic solution. It's not doing any, real measurement of time. It's just kind of like a priority flag that says that it will do things in orders with the smallest delay first. We didn't really apply this to our example, but you can see there's time delay on the action level. Here it is in the dialog. So if I go back here, I can see here's the time delay field for that action. And there's some slides that kind of get into the details of how that can be used. It can also be present on a model filter condition. And I'm not going to go into great detail, but it's in the slides for the reference. Here's like if you have a really complicated nested model filters inside of filters, then it'll determine the total delay based on what actions are taken, and then if it gets down to a certain point, it'll take the one with the smallest delay. We did use persistent contingency elements. So that was in our load drop, and it just went through in 10% increments until the condition that it was associated with was no longer met. And then this slide just goes through and shows kind of an overview if you've got a mixture of check and topology check and post check and solution fail, kind of the process that it goes through to evaluate all these things, and even incorporates time delays. We also have a contingency element called solve power flow, and you can incorporate that. Once you do that, then it does kind of impact the order of how things are solved. Model expressions, I mentioned these a little bit earlier. We don't have an example that uses them, but if instead of evaluating on like a specific line flow or an interface flow or a bus voltage, you want to evaluate on some like a sum or a product or some other mathematical expression of multiple quantities, then you could build a model expression in order to calculate that quantity, and then you could use that inside filters. Some details on that. And transient models, if certain relays, the conditions are met, you can have their actions taken in the contingency analysis. And then finally, the last few slides in here go through just some techniques you can use with our sensitivity analysis tools if your task is to determine what a remedial action should be. We kind of assumed that we already knew in the example that we just did. We knew that for certain loading levels, we were going to need to take certain actions. But if you're in a position to have to design these, like maybe operations planning engineers might have to, this just goes through the use of some of our sensitivity analysis tools like TLR or line outage distribution factors, our line loading replicator, our optimal power flow with a minimum control change objective function, and how you can use those to kind of identify controls that work. I'm not going to get into the details of this, but there is some examples that walk through this specific case and how you could calculate sensitivities on overloaded elements. And so here's line loading replicator, like if you want to figure out what controls to move in order to bring the line back down to its rating. And once you identify controls, you can just kind of play around with it in the power flow and see if you get the desired result. And then once you identify those thresholds, then you can build your remedial action scheme. Here's the optimal power flow with minimum control change objective function. And if you look at the results, we've got whole other training section that shows you how to use the optimal power flow. But you can look at the table results and see which generators are moved up or down by the OPF, and then those might be good candidates to put in a gen drop injection group.
If you need further assistance, please feel free to look us up on the web, give us a call, send email to our support line, or if you prefer to work with a particular Power World engineer, please feel free to contact that person directly.